Welcome again students. I am Sudipto Karmakar, Assistant Professor of Physics, SGIST, and in today's video we are going to derive Stefan's law, which is also known as Stefan's-Boltzmann law, from well-known Planck's law of radiation. So, we are going to learn the Planck's law of radiation in terms of frequency. So, according to Planck's law of radiation, the energy density of blackbody radiation for frequency range nu to nu plus d nu is E nu d nu equals to 8 pi h by c cube into nu cube divided by e to the power h nu by kt minus 1 into d nu. Okay, so this is the representation of blackbody radiation's energy density of blackbody radiation in terms of frequency. So here the parameters are: h is Planck's constant, c is velocity of light, K is Boltzmann constant, T is the absolute temperature of blackbody, and E nu, D nu is the energy density of blackbody radiation for the particular frequency range. So, if we try to derive Stefan's law of radiation or Stefan's law, then we need to integrate this energy density for all possible frequencies. Okay, so the total energy of blackbody radiation for all possible frequencies so we need to integrate this quantity. Okay, so for all possible frequencies, that means the frequency cannot be negative. So we cannot take the negative values. The frequency can be 0 and it can be of a large quantity or it can be of a large number. So theoretically the maximum value of frequency, it is infinity. Okay, so the total energy, that is capital E, that is equals to integrating this quantity from 0 to infinity, E nu d nu, that is equals to 8 pi h by c cube. It is a constant quantity, so I am keeping it outside of the integral sign. Integration from 0 to infinity, nu cube divided by e to the power h nu by kt minus 1 d nu. So we need to evaluate this integral. So to evaluate this integral, we are going to substitute the quantity h nu by kt by x. So here I am taking, let x equals to h nu by kt. Okay, now if we rearrange the quantities from both sides, so we have nu equals to kt by h into x. Okay, so if we take differentiation on both sides, so it results d nu, it is equals to kt by h dx. Okay, so we are going to substitute that h nu by kt equals to x and d nu equals to kt by h into dx in this particular integral. Okay, so we have 8 pi h by c cube integral from 0 to infinity nu cube, that means kt by h into x whole cube, right? So it is kt by h whole cube and also x cube. Now what about the denominator? In the denominator we have e to the power h nu by kt minus 1. So I am writing it as e to the power h nu by kt, that means x minus 1. Now what about this d nu? This d nu is nothing but kt by h into dx. So I am writing it kt by h into dx. Clear? Now if we take kT by h, since it is a constant quantity outside of the integration sign, then we have 8 pi h by c cube. We have kT by h cube and kT by h, that means kT by h to the power 4 integration from 0 to infinity x cube divided by e to the power x minus 1 dx. Okay. Now, so after simplification we have 8 pi k to the power 4 t to the power 4 by this h to the power 4 and h cancels out, leaving c cube h cube. Now what about this value of this integration? So this is a well known standard integral and its value is pi to the power 4 by 50. This thing is to be memorized. That is, the value of this integration, integral 0 to infinity x cube e to the power x minus 1 dx, its typical value is pi to the power 4 by 50. You need to memorize it. Okay, so keep it in your mind. So therefore, after simplification, we have 8 pi to the power 5 k to the power 4 by c cube h cube. Oh, there is a 15 also. 15 t to the power 4. Okay. So this is the expression for total energy. Total energy for all possible values of frequency. So we have evaluated the expression for the total energy of blackbody radiation from Planck's law of radiation in terms of frequency. Now we need to find the total emissive power of blackbody. Now the total emissive power means the total energy radiated from the blackbody per unit area per unit time. It can be shown that total emissive power of blackbody, total emissive power means the total energy radiated per unit area per unit time. I am denoting it as E prime. Okay. So it can be shown that the total emissive power of blackbody, it is equals to C by 4 times the total energy. Now, what about the total energy that we have already evaluated in our previous calculation, that is equals to 8 pi to the power 5 k to the power 4 t to the power 4 divided by 15 c cube h cube. So we need to multiply this quantity by c by 4. Now what is c? C is nothing but the velocity of light. So therefore the total emissive power E prime, it is equals to c by 4 into 8 pi to the power 5 k to the power 4 divided by 15 c cube h cube t to the power 4. That results this and c cancels out, this 4 and 8 cancels out, so it becomes 2 by pi to the power 5 k to the power 4 divided by 15 c squared, because this c and this c cancels out, so leaving 2 c squared h cube into t to the power 4. Okay. So this is nothing but, this quantity is nothing but Stefan's constant. This quantity is nothing but Stefan's constant. If you put the values of Boltzmann constant, velocity of light and h in this particular expression, you will find that it is numerically same as that of the Stefan's constant. Okay. So therefore the total emissive power, that means E prime, that becomes equals to sigma T to the power 4, where sigma is 2 pi to the power 5 k to the power 4 divided by 15 c square h cube. It is nothing but Stefan's constant. Okay. So therefore the total emissive power E prime, that is equals to sigma T to the power 4. It is our well known Stefan's law. So students, here we have derived Stefan's law from Planck's law of radiation. Hope you will find this video useful for your examination purpose. Thank you for watching. See you in the next video.